I will now describe an experiment to trace the phase transition in NITINOL, an alloy of nickel and titanium, which shows shape memory effect. Buehler discovered accidentally that an alloy of nickel and titanium at a particular composition, when dropped to the floor, makes a dull sound and not the sound that one hears from a metal. This alloy is super plastic. That means it can be deformed to a very large extent like rubber. At room temperature, this alloy could be plastically deformed to a much larger extent than any metal. One can make a coiled spring of this alloy at high temperature, cool it, it will remain a spring, and then you can stretch it to 2 or 3 times its original length. If the stretched spring is immersed in a beaker of water above 60 degrees centigrade, the spring comes back to its original length and shape. This spring remembers its original shape, so this alloy is called shape memory alloy. Why does shape memory effect occur in this alloy? Shape memory alloys are metallic alloys that undergo a solid to solid phase transformation, which can exhibit large recoverable strains, for example, NITINOL. At high temperature, the structure of NITINOL is the austenite structure. It is a cubic crystal structure with the nickel atoms in a face-centered lattice, the titanium atoms sitting between 2 nickel atoms. This is cubic, that means the angle between the A and the B axis is 90 degrees. When you cool it to room temperature, structure changes to the martensite form. This martensite form can be obtained from the austenite by shifting successive layers of atom by about 0.08 angstroms. The angle then becomes less than 90 degrees, and therefore it has a monoclinic crystal structure. The layer can be shifted to the right or shifted to the left. So in the twinned martensite, adjacent layers are shifted to the left and right alternately. So this structure looks like the bellow of an accordion, and you can stretch this structure to a very long extent. This explains superplasticity at low temperature. I repeat, high temperature austenitic phase is a face-centered cubic structure. The low temperature phase is obtained by shifting adjacent layers in the austenite structure by 0.8 angstroms. The resulting structure is monoclinic. One can shift the adjacent layers to the right or to the left. When both configurations are present together, we get a twinned martensite structure. This is a folded structure and can be extended by a large amount. When the sample is heated, it goes from the martensite to the austenite phase, and when it is cooled, the reverse transition takes place. This is a sluggish transition because it involves the cooperative movement of a large number of atoms. So when you heat the twinned martensite structure, the austenite phase starts appearing at this temperature, and the entire material becomes austenite at this temperature. There is a range of temperatures over which the forward transition takes place. When you cool it, the martensite structure starts appearing at this temperature, and the entire material becomes martensite here. So this is the start of the martensite transition. This is the finish of the martensite transition. This is the start of the austenite transition. This is the finish of the austenite transition. Because it involves the cooperative motion of all atoms, it is a sluggish transition. Transition does not take place at a sharply defined temperature, but is spread over a range of temperatures. So in the forward direction, the transition is complete at a temperature T end. In the reverse direction, it is complete at a lower temperature T dash end, which is lower than T end. So the transition shows a large hysteresis. The phase transition can be studied using any property which changes during the phase transition. Resistivity of a material is sensitive to changes in structure, and it can be easily measured. So resistivity measurement is often used in the study of phase transitions. We will use resistivity measurement to the study of this phase transition. This diagram shows the experimental arrangement. We have a constant current source. There is the constant current source. We have a power supply to heat the heater. This is the power supply to heat the heater. And we have a microvoltmeter to measure temperature as well as the voltage across the sample when a current flows from the constant current source through the sample. The sample is a ribbon of nitinol which is clamped between two heaters. Sample is clamped between two heaters here. There are current leads coming from the sample which are connected to the constant current source. There are voltage leads coming from the sample. The voltage leads are these leads. They are connected to channel 2 of the differential amplifier. There is a chromal-alumal junction which is in contact with the sample. The leads of the chromal-alumal junction come out, they are connected to channel 1 of the microvoltmeter. So I switch on a current of about 20 milliamperes. I turn this switch to channel 1. The differential amplifier measures the voltage across the sample. The sample here is not nitinol. It is nickel copper alloy which has a low resistance, and so the voltage is 158 microvolt. For the nitinol sample, the voltage will be about 5 millivolts. This shows the chromal-alumal thermo EMF. I switch on the power supply, set a voltage of 2.6 volts, then the thermo EMF increases rapidly. We adjust this voltage so that this rise is 40 microvolt in 1 minute. Then every 2 minutes we take the reading of the thermo EMF and then the voltage across the sample. We continue doing this till the reading on channel 1 comes to 2.2 millivolts. At that point, 2.2 millivolts. At that point, reduce the supply voltage so that the furnace starts to cool slowly at the same rate of about 1 to 1.5 degrees per minute. Continue taking the reading of channel 1 and channel 2 every 2 minutes till you reach a temperature close to room temperature. That is, channel 1 reading will be about 0 millivolts. The current through the sample remains constant. So the voltage measured at channel 1 of the microvoltmeter is proportional to the resistance of the sample. The temperature T of the sample is calculated from the microvoltmeter reading on channel 2 in millivolts. You multiply the reading in millivolt by 25 and add room temperature. That is the temperature of the sample. We plot the voltage measured in channel 2 against the temperature calculated from channel 1. This part of the curve shows the readings while heating. You see that the martensite to austenite transition starts around 60 degrees and is completed around 70 degrees. While when cooling, this is the curve, the transition starts around 55 degrees and is complete around 45 degrees. Shows a very large hysteresis. Curve clearly shows a drop in resistance as the temperature is increased. The drop starts around 65, transition is complete around 70. While cooling, resistance increases around 50, transition is complete around 40. Hysteresis is exhibited clearly. Shape memory alloys have found many applications in aerospace industries and in medical applications as stents for widening clogged blood vessels.